Welcome to lecture 54 on balancing oxidation chemical reactions. There's some very important steps that you need to learn. And the first one actually starts with understanding what is the oxidation state of each element in your chemical reaction. So we have a lead-off question: what's the oxidation state of manganese and the manganate ion here? And let's see what you can come up with. It's good to just pause the video for a second. And hopefully you got the oxidation state of +7. Now, if you did not understand how to get that, you need to stop. There's a separate video. There's other videos out there where you need to be able to figure out the oxidation state and relatively quickly of the elements in compounds and ions. So go watch that. Don't go any further. You need to know how to do that first. The rest of this lecture is based on you already knowing that and being quite quick at it. All right, with that said, we've got some aisle coming up that you're going to be doing a lot of balancing of these oxidation chemical reactions. All right, what do you got to do? First step in looking at a chemical reaction and balancing it is assigning the oxidation state, just what I just talked about. We're going to practice all of these things probably about 4 times in this lecture so you can get a good idea. Once you assign the oxidation states, you're going to be able to tell who's being oxidized, who's being reduced. We're going to split those two parts into half reactions, an oxidation half reaction and a reduction half reaction. Once you've done that, we're going to take each one of those half reactions and balance them. So make sure all the elements are balanced, then balance oxygen, balance hydrogen, balance charge. And then we're going to balance the number of electrons between the two half reactions, add them together and make sure everything's balanced together. So there's flow charts for doing this. We're going to write the separate half reactions, balance both of them, bring them back together. Okay, it's not too bad, and it's one of the nice things in chemistry that actually works well if you follow the procedure and lots of practice. Let's do our first one. We're going to keep it nice and simple for the first one. We got copper plus silver ions that react to give copper 2 ions that are colored in blue and silver 0, which is called silver solid. So what's the reaction that's going on here? Our first thing is to assign the oxidation states. Now this one's quite easy because if there's no charge written, it's 0. And if there's just a charge with a single element, then it's that charge. So copper is 0 and silver is +1, and then copper becomes +2 and silver is 0. Next, we need to assign who's being oxidized and who's being reduced. Well, the copper element is being oxidized, going from 0 to +2. It's increasing in its oxidation state. Silver is going from +1 to 0, and so that is our reduction. So reduction means lowering the oxidation state. It doesn't mean it's going to 0. It did in this case, but it just means it's going down. So the oxidation step is copper to copper +2, and reduction is silver +1 to silver. We'll put in the phases and states in just a little bit. Now we're going to balance the mass on each side. This one's pretty easy. There's already 1 copper on the left side and 1 copper on the right-hand side. That says an ion, but it's still just one of them. These are the numbers in front or in subscripts. Silver also balanced. Already done. Okay. Now, normally there would be other steps in here where we'd balance hydrogens and oxygens as needed, but we don't need to. So we're just going to focus on the charge. Now, copper is going from 0 to +2. Well, how does it do that? Well, we're going to balance that half reaction using electrons and electrons only. So in order to become positive, you have to give off electrons. And the way to do that is to have 2 electrons as products. This will now balance the charge on both sides of the oxidation half reaction. Silver then gains an electron to go from +1 to 0. So we can only add electrons here. No protons, nothing else, just electrons. These are the electrons that will be transferred in these electron transfer reactions. All right. Now the next step is to balance the number of electrons between both of them. So we're going to multiply the silver reaction by a factor, in this case 2, so that we have the same number of electrons being given off in the oxidation step and gaining in the reduction step. So I've added the new words here just to, as a review. Copper is the reducing agent because it gets oxidized. Silver ions are the oxidizing agent because they get reduced. It's important to remember the terms agents. We like to use those. Now we're going to add the two half reactions all together, put all the reactants together, copper plus the two silver ions, and then put all the products together, copper plus 2 ions and the 2 silver. Anything that's the same on the reactant side and the product side go away, and that's the 2 electrons. So let's add in the states here to make sure copper, if it's zero charge at its standard state, is a solid, and the ions are aqueous. All right, so now we're balanced by both charge, number of atoms, and we have successfully come up with a balanced oxidation reduction reaction. Okay, let's do one that's a little bit harder. Let's look at the reduction of vanadium oxide here ion with zinc. The vanadium compounds are beautiful. They have highly colored. These are transition elements with different oxidation states. So this is a good practice. So I have VO2 plus, VO plus, V3 plus, V2 plus. Can you figure out the oxidation state of vanadium in each one of these compounds? I'll pause to give you a moment to think about it. All right, let's take a look. What's the oxidation state of vanadium? And as part of that process, we assume oxygen's -2, and this works for 99% of the cases here. So if that's the case, if oxygen's -2, then vanadium in the first one is +5, +4 in the next one, +3 and +2. We can just use the charges there when, if there's no other element to worry about. All right, so let's take a look at this chemical reaction here. First step is to assign the oxidation state. We already figured out vanadium's +5 in the first one. And, oh, I forgot to write -2 for my oxygens on the left and right-hand side. The metals are typically where the oxidation reduction take place, but not all the time. So we need to be consistent, and I'll do that on the other ones for sure. So we see that vanadium is going from +5 to +4, so it's being reduced. Zinc is going from 0 to +2. That's increasing in its charge. That's oxidation. So let's write the half reactions, oxidation and reduction. And you just go ahead and split those elements into each side. Okay, the next one is to start balancing for the number of elements on each side, the main elements, like the non-oxygen, the non-hydrogen ones, okay? So zinc's already done, there's one on each side, and vanadium is done as well. There's just one vanadium on each side. But as you'll see, there is an oxygen, 2 oxygens on the left-hand side for the vanadium and 1 on the right-hand side. To balance oxygens, we're going to add water on the deficient side. So I need another oxygen on the product side to make sure that those are equal to each other. So our first step is to balance oxygens by adding water. Secondly, we're going to add hydrogen ions to the left-hand side to balance the number of hydrogens that I added by adding water. This is what we call balancing in acidic solution, which is the term I had at top. Acidic solution provides the protons, H+, that we need to execute these and process these electrochemical reactions. All right, now this chemical reaction, both of them are balanced by all their masses of the elements. So basically, you have the same number of elements on both sides. So if you're deficient of oxygens, you just add water, but then you got to balance out the hydrogens with protons. All right, the next step we're going to do is to balance the charges using electrons. In the oxidation step, which is losing electrons, that means you're producing electrons, you're giving off electrons. We're going to need 2 of those to balance out the +2 charge. So we now have 0 on the left-hand side and 0 on the right. Doesn't have to be 0 on both sides. We just want to do what's easiest to balance it on both sides. In this case, for the reduction, if we add just 1 electron, that will give us the same +2 charge on both sides of the chemical reaction. So it's not about getting to 0 on both sides, because then you'd have to add electrons on both sides. The other thing I would note that the reduction step is that we've reacted, we add an electron to the reactant side. Now we're going to multiply both or one of the chemical reactions by a factor so that we have the same number of electrons transferred. That's pretty easy. We just need to multiply the reduction one by 2, And so we're going to double everything. Once you've they scaled both reactions so they have the same number of electrons, you can just add them together. What does that mean? Add all the reactants together, add all the products together, and then we're going to reduce anything that's the same on both sides, which in this case is the 2 electrons. And it doesn't look like there's really anything else that we can cancel out. So we're good to go. We should add the states to that. Any ions are aqueous. Water, of course, is a liquid. Zinc is a solid. So should have added that to that. Okay, let's go to a really hard one and see if we can solve that. So how can we balance this chemical reaction right here between the dichromate and a sulfite ion? So this one's got quite a few oxygens in here, and we need to balance this one. Step number 1, what do? Figure out the oxidation state. So that'll let us know who's being oxidized and reduced. All right, hopefully you know how to do this for the chromium and oxygen. We're going to do that for all of them. And I see chromium's a +6, oxygen's a -2, and the sulfate's +4 and -2 for the 2 elements there. Chromium's a +3, and then goes to sulfur being +6 and oxygen's -2. All right, we see that. Who's being oxidized? Well, it looks like sulfur is going from +4 to +6. So we're going to use not just sulfur, but we're going to take everything that's with sulfur, that's the sulfite ion, and then react it to make the sulfate ion in the oxidation half step. And then it looks like chromium's being reduced from +6 to +3. Okay, so once we have identified the oxidation states, we're going to separate those two, and I'm actually going to work it out here. I said working on the board, that's what I would normally do in class. I'm going to just show you the answer, and we're going to see how this came up with this. Wait a second, how could we balance a chemical reaction and all of a sudden we gain things? Look, we gained 8 hydrogens and 4 waters. How is this possible? When you follow the steps, you're going to gain things that you cannot possibly have seen just by looking at it and balancing it. So this is what makes oxidation reduction reactions and balancing them very different from what we've learned before. All right, so we're going to include the dichromate ion as the reactant and then put the chromium that it converts into on the reactant side. So this is the reduction. I know before in other ones I started with the oxidation. It doesn't matter if you list the oxidation step first or the reduction, just get them right. And you can see that the sulfite is being oxidized and it's adding more oxygens. So that's also what oxidation is. So our next step is to balance the number of atoms. Oop, looks like I've already done that. And I've added 2 chromiums on the right-hand side to make sure it balances with the 2 chromiums on the left-hand side. Sulfur is already balanced. So I do those main elements first. I ignore hydrogen, I ignore oxygen in my first balancing of the atom step, okay? Our next step that we're going to do is to balance the oxygens with water, okay? So we can see in both steps that oxygen is not balanced. So we're going to need to add waters. Well, on the first step, where I've got 7 oxygens on the reactant side, I'm going to need to add 7 waters to balance that. And on the reduction step there with the sulfur, there's 3 oxygens on the left, 4 on the right. I'm going to need to add 1 water on that to balance it out. All right, so now that we see that, we've got our 7 waters. I've just added them to balance the oxygen. I just completely ignore anything about hydrogen. I ignore anything about chromium. I'm just laser focused on the oxygens right now. And I only needed 1 water because it adds 1 oxygen to my oxidation step with the sulfur and the sulfite and sulfates. All right, but I've created an unbalanced situation by adding in all these hydrogens from the water. So the next step is to add hydrogen ions on the opposite side of the water in order to balance all of those new ions, the extra atoms that we've added. So if I added 7 waters, I'm going to have to add 14 hydrogens on the opposite side to that. So that's here we show that step. So our goals now is to be laser focused on the hydrogens, ignoring everything else. Ignore charge, ignore oxygen, ignore chromium. Don't worry about any of that stuff. Laser focused on the hydrogens. And then, since I added 2 waters there, I'm going to have to add 2 hydrogens, 2 protons here on the right-hand side of the oxidation step. That balances all the hydrogens. So now in both steps, I have balance of elements. The main element that's switching, changing, oxidizing, reducing, balance the oxygen, balance the hydrogens. Now, once we've done that, our next goal is to balance the number of charges on both sides. Where it's about balancing. The goal is to balance them, and not to worry about getting both sides to 0. Balancing the charge, and we can only use electrons. So in order to do that, I need 6 electrons to balance the charge on the first reaction. Now, why is that? Well, you can see if I had just the 14 hydrogens and the -2 from the dichromate, that would give me a 12 plus on the left-hand side, the reactant side. And it is 6 plus on the right-hand side. So in order to go from 12 plus to 6 plus, I'd have to have 6 electrons to be reduced there. Okay, pause the video, look at the steps. Why did I add 6? Can you see that? Ask questions if you're unable to figure this out. And the next one, I needed to add 2 electrons. Why? Well, I can only add electrons, and it's the oxidation step, so they're going to lose them. Notice how I gained them in the reduction step. And this will always take place. In the oxidation step, I had a -2 on the left-hand side, and basically it was neutral with the -2 plus 2. And so I need another extra 2 electrons to get a balance on both sides. Remember, it's about balancing charges using electrons, not about getting to 0 on both sides, okay? Just balance, and I can only use electrons. All right, now that I have both half reactions balanced in both elements and charge, I need to get the same number of electrons to be transferred in both of those. So I'm going to multiply the oxidation step by 3, so that gives me up to 6 electrons transferred on both sides. So I'm just going to now multiply by 3 and then add both of them together. That means putting all the reactants together. Now I had 3 waters from the sulfate, the 3 sulfites, 14 hydrogen ions, 6 electrons from the top there, and the dichromate. And on the product side now, 3 sulfates, 6 electrons from the oxidation step, and then I'll have, and then 6 hydrogens, and 2 chromiums, and 7 waters from the reduction step. I'm going to look through and see if there's anything that's the same on both sides. Clearly the electrons, 6 electrons on both sides. I can subtract 6 electrons from the whole thing, and those will go away. I see that I've got hydrogen ions on both sides and water on both sides, and I can reduce water by 3 on both sides and the hydrogen ions by 6 on both sides. And that gets me down to this final overall chemical reaction. You need to pause and see how those steps took place, how I reduce those down. Hopefully that is getting a little bit easier for you. All right, our last one, well, I should just say this one was balanced in acid. That was our main focus. We used hydrogens to balance the waters. That's what it means to balance in acid. Now you may get asked sometimes to balance something in basic solutions. And I'm going to show you an easy step how to do that. Here is this chemical reaction, the bromide ion plus the manganate permanganate ion reacting together to get bromine as a liquid and the manganese plus 2. We're going to balance this one using basic conditions. How are we going to do that? I like to show the answer to begin with. We're going to end up with this complex answer right here. And you'll see that there's base that was added, ends up being produced. We end up with water and hydroxides that are just not visible by looking at it. You cannot just grab these things and throw them in there. You have to go through all of the steps. Now, in order to do this in basic solution, I have one simple trick for you to do this. And the simple trick is balance an acid. That's right. But it said base. Yeah, acid's way easier. Trust me on this. I've tried to do it always. The best way is to go through and get a final chemical reaction balanced in acid. And then we're going to do one switch at the end to base. It's pretty easy, but let's do our balancing in acid because that works really well. Okay. So we go through and we assign the oxidation states for each one. Bromide, it's -1, so it's -1. The permanganate there is +7, oxygen's -2. Bromine as a liquid is 0, and then +2 there. So who's being oxidized, who's being reduced? Well, I see the bromine atoms going from -1 to 0. So that means bromine and anything included with those is oxidation. It looks like manganese is going from +7 to +2. So that's our reduction. All right, so we put all of the elements that are associated in those compounds and ions with the permanganate ions and the manganese. We put those into our oxidation and reduction half steps. Okay, then we balance masses. This is not too bad. We just need, looks like 2 bromides on the left-hand side, the reactant side, to balance with the 2. There's already just 1 manganese on both sides, so there's nothing to do there. Once you balance the mass of the atoms there, we're going to go, now we go after the oxygens. So the first step, there's nothing there we need to do. There's no oxygen, so we just leave it. Next step with the permanganate, we need to add 4 waters on the product side to balance the 4 oxygens that were on the reactant side. Okay, now we're going to balance hydrogens. Nothing needed in the oxidation step. We didn't add any water. No need to add hydrogen ions. Don't make stuff up. Since we added 4 waters, we're going to now add 8 hydrogen ions to balance those out. All right, just checking the time here. We're doing good. Now, once we've balanced the hydrogens, we're going to balance the charge. And the way do we do that is add electrons, especially in the oxidation step. Those better end up on the product side. So we need 2 of those to get 2 negative charges to balance the 2 negative charges of the bromide. We're going to end up adding 5 electrons to the reduction step and a gaining here on the product, on the reactant side. That'll get us to a, so we have a +8 with the protons, 5 electrons, and the -1 charge on the permanganate ends up with a +2 on both sides. So now we're going to scale each reaction. So they'd have the same number of electrons transferred. This is like a common factor or common multiple. What's a common multiple? Well, 10 is a common multiple between 2 electrons and 5. So I'll multiply the first one, the oxidation step, by 5 and the reduction step by 2. Okay, I mean, you got to do it to everything. You can't just multiply the electrons. You got to multiply every single item in that chemical reaction by 5 and every single element and electron by 2 in the reduction step. Okay. Multiply them through and combine them. Okay, so I'm just putting all the reactants together now and all the products together, and you'll see that I have 10 electrons on both the reactant and the product side, so I can get rid of those. And any waters or hydrogen ions and get rid of? Nope. So now what do I have here? I have 16 hydrogens. All the electrons go away. So once you've got it finalized in acid, the new trick here to balance in base, this is the very last step here. We're going to add hydroxides to get rid of the hydrogen ions. So for every hydrogen ion, you got to add a hydroxide. But whatever you do to one side, you got to do the other side. So if we're going to add 16 hydroxides, you can't just add them. You need to add them to both sides. It's kind of like a math equation. If you add one thing to one side, you got to do it to the other. So we're going to add 16 hydroxides to balance out the 16 hydrogen ions. I was just focused on that part. So I add 16 to both sides. And we're going to do a little chemical reaction in our head that says for every 16 hydrogens plus 16 hydroxides, that's going to make me 16 waters. Okay. So now we got 16 waters on that side, and I have the new 16 hydroxides on the product side. Now I look to see if I can cancel anything out, and you should be able to reduce some waters. And I can reduce 8 from both sides. So that gets me now to 8 on the reactant side. And now I've gained the 16 hydroxides. And this looks like my new final chemical reaction here with all the states and charges. Double check everything, and that's good to do. And just to go back to our original slide here, sure enough, we end up getting this new final chemical reaction that matched what I had stated that it was going to be. And in the process of balancing, you gain waters, you gain the hydrogen ions, and then you switch the hydrogen ions to base, to hydroxides by doing that process. Follow the steps. Don't skip the steps. Don't try to do it and thinking through it, like guessing it. Just follow the steps. Here they are again. This is how OWL states it, and it's a good set of examples here. Assign the oxidation numbers, separate into the steps, balance everything except the hydrogen and oxygen, then balance the oxygen using water, balance the hydrogen with hydrogen ions. Go through, follow the steps, add electrons to balance charge, and then balance the number of electrons on both half steps there, and then reduce any common numbers. If you need to do it in basic solution, after that very last step, we're going to add hydroxides. So we're just finalizing everything there together, and these are the last few steps there. A couple of tips just to make sure: we're only adding water to balance oxygens. We're not going to add O2 or just plain old oxygen atoms or 2 minus. It's just water. Okay, water will provide our oxygens. Hydrogen ions will always provide our balance in hydrogen ions. We're not going to add H2 or 8 hydrogen atoms. Okay, make sure you write down and you figure out the oxidation states and you get all the correct charges on the ions there. Check your work as you go along. Practice, practice, practice. And if you follow those steps, you're going to be able to do this. This is doable. Practice, get some help if you can't get those oxidation states figured out. And I hope you've learned a few things from this lecture on balancing oxidation reduction chemical reactions, redox. You can do this electron transfer chemical reactions. We'll talk to you later.